Thank you for the introduction. Good afternoon. I'm Seongmin Kim from KAIST. Today, I will present our work, Enhancing Security and Privacy of Tor's Ecosystem by using Trusted Execution Environment. This is a joint work between Georgia Tech and KAIST. Tor is the most popular anonymity network for Internet users. It helps users to keep their private information, such as what sites they visit and their IP addresses. Since it is practical and freely available, it currently serves 1.8 million users on a daily basis. Tor provides freedom of speech for activists and journalists from oppressive government and regimes. Therefore, protecting the privacy of Tor users is critical. However, there have been many attempts to break the anonymity of users for a decade. We see many examples of threats on Tor. Tor provides sender anonymity based on three-hop onion routing. When a client tries to connect the server using Tor network, it first chooses 3 Tor relays. Then, it incrementally builds an encrypted circuit based on TLS communication. Therefore, a single Tor entity cannot know both source and destination. Since Tor is a volunteer-based network, Tor relays are not trusted by design. In the current Tor's threat model, it assumes an active attacker who can operate his own Tor relays. Also, he can compromise some fraction of relays. Finally, Tor assumes an adversary who can observe some fraction of Tor traffic. Tor tries to mitigate the threats in 2 ways under this assumption. First, it has a centralized entity called directory authority. The directory authority exercises a careful admission of new relays through vetting process. Also, it probes potential malicious relays and performs bandwidth scanning to detect the malicious behaviors. Fundamentally, an attacker can break the anonymity if all relays in a circuit are compromised. To avoid such situation, Tor maintains a large number of relays. It lowers the probability of choosing malicious relays by clients during the circuit establishment. In contrast, Tor does not address a network-level adversary who controls a large fraction of network. Currently, Tor runs more than 10,000 relays. Therefore, compromising a large fraction of relays is very hard. Moreover, it is generally believed that large-scale traffic analysis is non-trivial when the number of users and Tor relays are large enough. However, Tor is still vulnerable to many types of attacks under its traditional threat model. The first problem is the lack of fundamental trust bootstrapping mechanism. In the current model of Tor, Tor relays are semi-trusted by design. The directory authority cannot fully verify the behaviors of relays. In fact, many attacks are discovered and reported after the fact. Additionally, an attacker can gain advantage by simply running a relay. For example, he can get the sensitive information such as circuit identifier, and even he can modify the behavior of relays. In other words, having a few Tor relays is enough to break the anonymity of Tor network in some cases. We call attacks assuming such a condition as low-resource attacks. By utilizing a combination of multiple factors, many previous studies show that the anonymity of users can be broken. Tor multiplexes multiple circuits in a single TLS connection and multiple TCP streams in a single circuit to improve efficiency and anonymity. However, once an attacker runs a Tor relay, the circuit level information is visible to him. Demultiplexing a circuit is trivial since attackers can decrypt the TLS connection and can get the cell header. The cell header includes the circuit identifier that specifies which circuit the cell refers to. In fact, many attacks rely on being able to identify circuits. Moreover, since attackers can modify the behavior of relays, they can modify or inject the cell. It helps them to correlate the Tor traffic. If an attacker modifies the relay to give false bandwidth information to other Tor components, it makes a malicious relay to attract more clients. Therefore, the fundamental trust bootstrapping mechanism is required to address these problems. Also, providing a method to verify untrusted remote parties will improve the trust model of Tor. Then, the question is, how can we achieve this? In this work, we propose an approach that leverages trusted execution environment on Tor. Trusted execution environment, called TEE, provides a hardware-based mechanism for trusted computing. During the execution, the secure container protects the code and data of the program, even from the privileged software. Also, it is possible to detect the modification on the program by checking the integrity. Therefore, TEE can offer the fundamental low-level trust to protect the secrecy of Tor while ensuring its integrity. Among the commodity TEE technology, Intel SGX is the promising one. It gives native performance to software running in the secure mode. Currently, SGX functionality is available on several models of Intel Skylake and Kaby Lake CPU. So we developed SGX-Tor that applies SGX technology on Tor network. We ask ourselves two fundamental questions. First, what is the security implication of applying SGX on Tor? Second, is the deployment possible to the current Tor network? As an advanced trust model, SGX-Tor explicitly spells out what users trust in practice instead of placing implicit trust on Tor relays, and provides ultimate privacy due to the mixin model. Also, it protects the sensitive information and denies the modification on Tor relays. SGX-Tor increases the chance of having more hardware resources donated since it uses commodity TEE technology. We make SGX-Tor compatible with the vanilla Tor and incrementally deployable. In this study, we show that SGX-Tor reduces the power of an attacker who currently gets the sensitive information by running Tor relays. In other words, SGX-Tor raises the bar for Tor adversary to a traditional network-level adversary who cannot get any information other than passively observing the TLS byte stream. To understand how SGX-Tor works, let's see more detail about the memory protection mechanism of SGX. Using SGX, an application can keep its data and code inside the secure container called enclave. An enclave is mapped to the encrypted memory region called enclave page cache. The content is only decrypted by memory encryption engine inside the CPU package using processor-specific keys. Thus, even if a malicious adversary has full control over the hardware, it cannot access or modify the data. Also, the enclave is protected from other software running in the host, including the operating system and hypervisor. This means that an attacker cannot get any Tor-specific data from the Tor program running inside the enclave. Another key functionality of SGX is remote attestation. Using remote attestation, the host enclave can check the integrity of the enclave running in the remote platform. Additionally, it verifies whether the target enclave is actually running on the real SGX CPU. Before explaining our approach and SGX-Tor design, let's take a look at the threat model of SGX-Tor. Instead of trusting the application and the system software that hosts Tor relays, SGX-Tor users only trust the underlying SGX hardware and Tor code itself. Following the attack model of Tor, we do not address a network-level adversary who can perform large-scale traffic analysis. Note that attacks assuming vulnerabilities in Tor codes and SGX side channel attacks can be mitigated by recent studies. Here is the design and implementation of SGX-Tor. In the figure, the blue-colored box means the modified components from existing Tor, and the gray-colored box means the newly added components. We build a careful design to address several issues raised by leveraging SGX on Tor. The enclave memory of SGX-Tor consists of Tor core operations and SSL library for crypto and TLS communication. We modify SSL library to securely obtain the entropy within the enclave and the time value from the platform service enclave, which is a trustworthy source provided by Intel SGX. Also, it has a attestation module to verify the integrity of Tor program and sealing module for temporarily storing the sensitive data outside the enclave. In the untrusted region, SGX-Tor has an SGX runtime library and the rest of Tor operations which are not sensitive to Tor's security and privacy. As we mentioned in our threat model, SGX-Tor does not trust the operating system. However, Tor must rely on system software to handle several operations that require system calls. Therefore, a trustworthy interface between the enclave and an operating system is required. For this, we leverage eCall and OCall interface, which are provided by Intel SGX SDK. Here, a function that enters the enclave is called an eCall, and a function that leaves the enclave is called an OCall, respectively. We use eCalls to bootstrap Tor enclave, while OCalls are used to request service to system software. For each OCall, SGX-Tor performs sanity checking to validate the length of pointer variables and their address range. It prevents potential threats by malicious operating system, such as providing bad return values in system calls. In addition to providing the narrow interface, we harden the interface. SGX-Tor relies on minimal system support for networking, threading, and memory allocation. We implement 57 OCalls to make interface narrower, and the detailed types of OCalls that we implemented are listed in our paper. Let me show how SGX-Tor defeats low-resource attacks with examples. A tagging attack is a type of traffic confirmation by changing the behavior of the one end for it to be recognized by the other. For example, an attacker can detect a distinct pattern by duplicating existing cells or counting how many cells are sent over the network. This is used to effectively de-anonymize communications between two parties. Another example is a bandwidth inflation attack, which is used to increase the success ratio of low-resource attacks. When a malicious relay falsely reports its bandwidth to the directory authority, the authority advertises inflated bandwidth information to Tor clients. Since the relay selection algorithm of Tor depends on the bandwidth status of Tor relays, a malicious relay would attract more clients during the circuit establishment. However, such attacks are mitigated by SGX-Tor, since attackers cannot access the internal data such as circuit identifier and cells. If an attacker modifies the code to inject cells or inflate the bandwidth, it fails to pass remote attestation. In the paper, we have more details on how SGX-Tor mitigates many low-resource attacks. SGX-Tor also provides a new functionality that helps Tor community to manage relays more efficient. When a new Tor relay requests an admission to the directory authority, it first performs remote attestation to check the integrity. Note that Tor uses the same binary for directory authorities, Tor relays, and client proxies. If the target relay is not SGX enabled or fails to pass the attestation procedure, it is rejected. Therefore, the consensus document only contains the list of trusted relays that run SGX-Tor. This feature improves the trust model of Tor, since it explicitly spells out what users trust in practice. Here, the entire process is a one-time cost, so directory authorities can save the computation power to monitor the behavior of relays and can maintain more relays. Therefore, it improves the scalability of Tor network. To make SGX-Tor practical, we also address the incremental deployability. So far, we primarily consider the network that every Tor components are SGX enabled. However, SGX-Tor supports interoperability. For example, it is possible to establish a circuit that runs with an entry guard that runs SGX-Tor and the middle and exit, while the middle and exit runs original Tor. We had configuration options to enable or disable remote attestation. For SGX-Tor client proxy, we add an additional option to get the list of validated relays from SGX-enabled directory authorities. Without these options, SGX-Tor behaves like an ordinary Tor. In other words, we provide an incremental deployability of SGX-Tor to Tor's ecosystem. We implement SGX-Tor for both Windows and Linux environment and make it publicly available at GitHub. Additionally, we ported several libraries that are required by SGX-Tor, such as OpenSSL and libevent. We also compared the trusted computing base size of SGX-Tor with previous SGX studies that port OS functionality. Since SGX-Tor does not contain the whole library operating system, it has 3.8 times smaller TCP size compared to recent studies. We evaluate SGX-Tor by answering 3 questions. First, what kind of data of Tor is protected by SGX-Tor? And we show the performance overhead of using SGX-Tor. Finally, we verify whether SGX-Tor is compatible with a vanilla Tor and incrementally deployable. The table shows the data structure that are visible to current Tor, network level adversary, and SGX-Tor. In contrast to the current Tor, an attacker can only see the TCP IP header and TLS encrypted bystream by observing Tor traffic. In summary, SGX-Tor raises the bar for Tor adversaries to a traditional network level adversaries. To evaluate the performance of SGX-Tor, we construct a private Tor network in WAN setting. For the realistic scenario, we vary the location of relays. As the figure shows, we run an entry guard in KAIST and an exit relay in Georgia Tech. For middle relays, we use Amazon EC2 Cloud, which are physically located in Europe, US West, and US East. We measure the file transmission throughput and time to first byte of SGX-Tor and the original Tor. The result shows that SGX-Tor has 11.9% performance degradation and 3.9% additional latency compared to the original Tor, which is moderate overhead. We also evaluate the end-to-end client performance of SGX-Tor. For this, we measure the web page loading time while visiting Alexa top 50 websites in the same evaluation environment. We also launch a hidden service, which is a simple HTTP file server, and measure the throughput. As the figure shows, SGX-Tor has an acceptable performance overhead for both web page loading time and the hidden service performance. Finally, we verify whether SGX-Tor is compatible with a vanilla Tor and works correctly. We admit SGX-Tor relays in the existing Tor and collects results for 2 weeks. As the leftmost figure shows, SGX-Tor relay serves Tor traffic well. Also, it is selected as a middle relay by multiple Tor users. Finally, the SGX-Tor relays are listed in the published consensus document. It also acquires the fast and stable flags similar to the original Tor. Therefore, the result highlights the fact that we provide an incremental deployability of SGX-Tor. To summarize, we design and implement SGX-Tor by leveraging commodity TEE technology and demonstrate its viability. Using SGX-Tor, it is possible to establish an advanced trust model and protect the privacy of Tor users. As we provided SGX-Tor as an open source, we believe SGX-Tor has great potential for communities to spark new research on Tor. Thank you for listening, and I'm glad to take questions.
So we're already a little over. I'll allow one fast question and one fast answer, please.
Raluca Popa, UC Berkeley. Great work. Really fun application of SGX to Tor. I have a question about a class of attacks on SGX and whether they apply to your system. And those are the attacks on memory access patterns, such as the control channel attacks of Xu et al. That basically show that even if the memory is encrypted, the attacker still sees what you fetch from memory. And I'm wondering, so for example, if your circuit ID is encrypted, the attacker can see the patterns of memory accesses leading to accessing the circuit ID or the timing. So I wonder if your system is vulnerable to those kind of attacks.
Actually, I know the SGX controlled side channel attack, and in the current study, there is called TSGX, which protects the controlled side channel attacks to mitigate such attacks. So I think applying such methods to SGX-Tor would protect the kind of such side channel attacks.
Okay, thank you.
All right, thanks Seongmin again.